All right, I think we are all ready to go here. So let's get the quizzes got graded. They were actually pretty good. All of the errors that I saw were very, very small. So we'll take a look at this once they all go back. I do apologize for mangling your quiz, but my bike lock doesn't like to come out of my bag. So we'll take a look at that real quick. The off-campus students do not have their quizzes graded yet because I don't love them as much as I love the on-campus students. Either that or I had to fix their quiz on the fly too, and I don't have a solution for it yet because the solution manual for the homework assignment took me until, well, including stopping for dinner, it took me until about 11 o'clock last night to get that done and scanned, and it didn't help that there were at least 2 errors in the solution manuals provided by the publisher and stuff. So that's fun. We'll have to look into that. But yeah, so the plan for today, we'll take a look at the quiz. We'll finish up the AC analysis stuff. We will do a quick review for the exam, and then we will do the final quiz at the end of the class. The exam, as we'll discuss again at the end of the class, is going to be, it's Monday night, it's from 6 to 7:30, and it's, in the same classroom that we had it before in IRC 214. So I'm going to write the exam to hopefully be a little bit shorter than the last one, and pretty straightforward, so that'll be the goal. And I will put up some homework problems for Chapter 8, but I don't know when I'll make those due, probably something like next Wednesday or something like that. But all right, so let's go ahead and get moving on this stuff. So the quiz. Again, like I said, the quiz scores were actually quite good. All of the errors were very small. And here's the modified circuit that we worked with, just so that there was something. So the switch closes at time t equals 0. We have a 6 milliamp source. We have a 3K resistor, 6K resistor, 3K resistor, a half of a Henry on that, and a 3 kilo ohm resistor up on the top. So first step is to take a look at what the circuit looks like at time equals 0 minus. I'm not going to put in all of the circuit components because it's really not a big deal here. It was designed to be pretty much as easy as possible. And so when we look at this original, the circuit at time t equals 0, essentially you just have a current division to do. There's one current that divides between 2 parallel branches of the circuit. And it doesn't matter that this resistor is here because that current has to go through there and then will divide between these 2 branches. So there's 6 milliamps of current. The 6 milliamps of current coming through, and you put the other branch of the circuit than the one that you're interested in, so that's going to put the 3K on top over 6 plus 3, and that's these 2 resistors, which gives you an initial current through the inductor of 2 milliamps. So after the switch closes, we will have a circuit that looks more like this. Whoops, the arrow is going the other way. Of 2 milliamps, this one's 6 milliamps, 3K, 6K, and up here you got another 3K. And the voltage across that 3K resistor here is the one that we're interested in. We know both of the currents that are running through there. If you look at this in terms of a loop analysis, there's a current I1 going this way and a current I2 going this way, and we don't need to figure anything else out. They're just, those are the two currents. So you've got 3K times I1 minus I2 equals V sub 0. And I1 is 6 milliamps. This is 2 milliamps, so it's 3K times 4 milliamps, or 12 volts. And that equals V sub 0 at time 0 plus. One of the things that I did see on a couple of quizzes was then what happens to the 2 million, or to the inductor, because people would properly solve for I sub L here, but then when they drew the circuit, so this was the circuit at time equals 0 plus, when they looked at the circuit at time equals, or time greater than 5 tau, they would replace this inductor with an open circuit for some reason, and that would screw up their analysis. So you replace that under steady state DC conditions. The inductor acts as a short circuit. So 5 tau. So let's flip this over. We have the 3K resistor up on the top. We've got the 3K resistor, a 6K resistor, 3K resistor, 6 milliamp source, and nothing over here. This branch doesn't short anything out in particular. It really just kind of pulls these two things so that they're very clearly in parallel, and then that's kind of, let's see, then that series combination, or that parallel combination is in series with that, and then in parallel with some other things. And it's a, nothing gets shorted out is the kind of the bottom line there. 3K up on top, 3K here, 6K here, 3K here. We're solving for the voltage V0. And so I just did a mesh analysis to solve for the current that's running through here. Current I1 here, current I2 here, and current I3 here. So I1 just equals 6 milliamps. The voltage V0 that we're looking for will equal 3K times I1 minus I2 whenever we solve for those things. I'm just going to put down the original forms of the equation and then the solution. So we write out around the second loop, you have 3K I2 minus 6 milliamps plus 6K I2 minus I3 equals 0. Around the third loop, you have 3K times I3 plus 6K times I3 minus I2 plus 3K I3 minus 6 milliamps equals 0. So those are your two mesh equations. You solve for the currents, I2 and I3, and they respectively equal 4.5 milliamps and 3 3/4 milliamps. So we take this, we plug it in here, and you get that V0 equals 4.5 volts. Now one of the things that I double-checked when I double-checked the answer was figuring out what the Thevenin resistance looks like. And this one I actually had written down the wrong answer initially. And I'm pretty confident on this now. So one of there were a couple of things that I saw people do wrong here. One was to look at the Thevenin resistance, whoops, that's the 6K, to look at the Thevenin resistance from the point of view of the this 3K resistor that was that we were finding the voltage across. And you don't do that. You always look from the point of view of the storage element. So we're always going to be looking in from here to find our Thevenin resistance. We also need to make sure that we properly deal with zeroing out the current source, and it doesn't get short-circuited, it gets open-circuited. So there's just kind of a hole in the circuit. And so if you look at it like this, I think it's a little easier to see that these two 3K resistors are in series, and that series combination is in parallel with this 6K resistor. And once you combine those three resistors into a single resistor, you just have the 3K, the two 3Ks in series gives you 6K. In parallel with the 6K gives you 3K again. And so you have 3K and 3K in series for a total Thevenin resistance of 6 kilo ohms. Yeah?
So when you use that, you don't have to have like a complete circuit going around for those, the two 3Ks? Like, because I wasn't counting those because I figured, well, where the current go back, get back to the other side.
No, you don't have to have like a complete circuit. You look at it and say, oh, if I start combining these things down, what happens? So you take these are in series with each other, and that once you start messing around with the circuit, you can see that if you did hook up a source, there would be a nice complete circuit up here, just because there's these little terminals that the voltage or the current source used to be hooked up to. That doesn't kind of make those go away somehow. So, and I think actually I originally had the same answer that you did, and I went back and I double checked, and I'm 99% confident this is right. So, here's where I made another little. I always forget that whenever I make these problems and I choose the value for the inductor, that it's L over R Thevenin and not R Thevenin over L. So this ends up turning into an extremely small number. So it's 0.000083 seconds when you plug in the values of a half over divided by 6,000, which is a fairly large number. And so, let's see, K1 equals the value of V0 at infinity. K2 equals V0 at 0 plus minus V0 at infinity. And so that equals 4.5 here, 7.5 here. And the final form of the equation, VT equals 4.5 plus 7.5 e to the negative t over 0.000083. So here is a circuit that settles down extraordinarily quickly. So when, let's see, tens, hundreds, thousands, 10,000s, in 8/100ths of a second, the circuit pretty much settles down. Well, I guess multiply that by 5. But so for the online students, I'll get a solution guide put up for you guys and post it online, and I'll post it on the website for you on-campus students too, so you have a couple of extra problems to look at and play around with, and cursats and custom whatever. So, if you have any questions about the way that the problem worked out or the way that I graded it, please let me know so that I can do something about that for you. So, all right. Let's see. We need to finish up what we were doing yesterday, which was looking at a circuit with a bunch of different kinds of AC analysis. We did the nodal analysis, we did the mesh analysis, and now we need to look at the Thevenin analysis. And I think that we also have also doing it using superposition. And then we've got a circuit that we'll do a couple of different ways with that has dependent sources in it, because dependent sources are at least as important as in AC circuits as they are in DC circuits. So, where my markers go? All right. So the circuit that we've been working with was this guy. It has 1 ohm resistor. Whoops, that is an inductor. All right. Start over. Resistor, inductor. Current source. Voltage source. Resistor. Resistor. Capacitor. So here's our circuit. This is a 1 ohm resistor, a J1 ohm inductor, a 2 0 amp current source, a 6 at 0 degree volt source, a 1 ohm resistor, and a negative J1 ohm capacitor. And the component that we're solving for is the current I0. And in all the times that we've solved for it to this point, we've always gotten 2.92 at an angle of negative 30.9 degrees amps. And so that's what it should continue to be as we go through. We've gotten that 2 times. We'd like to get it another 2 times. So, just to show you that superposition works, and I did end up using superposition on, I think, 2 different problems last night when I was generating the solutions, because the stuff that they did in the solution manual was like pretty much useless. It was almost impossible to follow. And so, let's use superposition in the AC circuits and see what happens there. First thing to do is to short out. We're gonna short out the voltage source. So we've got a short here, we've got resistance, and we've got resistance and a capacitance. And so this is a pretty straightforward circuit. C1, 1, negative J1. And essentially we can just do a current divider to figure out what it is, as long as we combine the 2 outside branches in parallel. Get it down to just one. Get it down to 2 branches so that we can do a simple current divider. So the equivalent parallel resistance of the 2 outside branches will be 1 over 1 plus J1 plus 1 over 1 minus J1. And here's where we need to work on this. Start firing up the calculators, making sure we can do our complex arithmetic. So 1 over 1 plus J1 plus 1 over 1 minus J1. And then flip that, and we get 1. So the parallel resistance, so we can kind of smush this down into a slightly smaller circuit where we've got an impedance over here, which is the parallel impedance, and that just condenses down to a single ohm. And then you've got the current source, and then you've got over here original resistor that we were playing with in the first place. So here we don't actually have to do a whole lot of work, because we found that, well, there's I did that twice. There's 2 1 ohm resistors, 1 on either branch, so the current's going to divide evenly between the 2 of them, and the contribution from that original source is going to be 1 at an angle of 0 degrees amps. Now we take a look at it as by opening up the current source, reinserting the voltage source. We've got the 1 ohm resistor, the inductor, that's opened. Voltage source, minus plus. Voltage, or the 1 ohm resistor, J1, 1, 1, negative J1. So what is probably useful here is if we can bring this down to a single loop circuit, then we can find out what the current is that's running around and the voltage across the equivalent impedance of these three elements will be the same voltage that's across the 1 ohm resistor. We can divide that by, and then use that to find out what the current is that's actually across the 1 ohm, or going through the 1 ohm resistor. So to combine these into a single equivalence impedance, we'll have 1 over 1 plus 1 over 1 minus J1. And then we'll flip that, and that will give us our, call it Z prime P. So 1 plus 1 over 1 minus J1. And flip that. So you get 0.6 minus J 0.2 ohms. So that's the equivalent impedance. Let's replace this circuit. Let's even just make it a little simpler. Here's the 1 plus J1 of the resistor and the inductor. Here's our 6-volt source. Here's the other impedance, which we calculated as 0.6 minus J 0.2. And that's all the circuit's left with, 6 at an angle of 0 degrees. So divide the overall 6 volts by the total impedance, which will be 1 well, let's just put it in 1 plus J1 plus 0.6 minus J 0.2. And oh, I guess we can do it that way. In my notes, I actually have it done as a voltage divider, but we can do it this way. It's essentially the same thing. So 6 at an angle of 0 divided by 1 plus J1 plus 0.6 minus J.2. Gives us, this probably doesn't have a nice, just for convenience sake, we're going to leave this as 3 minus J 1.5, and that is the current that's running around the circuit. So the voltage across this particular element, let's call it V0, equals the 3 minus J 1.5 amps times the 0.6 minus J 0.2 ohms of resistance, or of impedance. So 3, 1.5 times 0.6, negative 0.2. Oh good, we're still getting the right answer. And so that is, again, for convenience and accuracy, this actually works out to 1.5 minus J 1.5, because as a phasor, that is not a very nice number. It's 2.12 and some junk at an angle of negative 45 degrees. So that is, and then the current I0 double prime that we've been solving for is just 2.12, an angle of negative 45 divided by 1. So 2.12 at an angle of negative 45. So the overall current I0 will equal I0 prime plus I0 double prime, which is 1 at an angle of 0 plus 1.5 minus J 1.5. So we add those up, 1 plus 1.5 negative 1.5 amp, we get 2.92 at an angle of negative 30.96 degrees. So continues to work out for us. Okay, so superposition still works, no big deal there. I guess I can leave that up while people finish writing. All right, last one. Here's doing the same circuit as a Thevenin equivalent. So kind of skipping over the original drawing of the circuit. Here's removing the load resistance already. And so the first thing to do is to calculate what the I hate when I do this. Is to calculate what the open circuit voltage is. One of the things that we haven't talked about a ton is the fact is doing this thing called source transformation. I don't remember covering it a ton in my own circuit classes when I was a student, and it's something that I've not found to usually be a terribly interesting or helpful kind of analysis technique. But in this case, it does make the analysis almost trivial. And we did talk about it just a little bit, which is the fact that if you have a Thevenin equivalent, you can create a Norton equivalent very quickly and easily. So here is my 2-minute digression on source transformation. If you have some voltage source and a series resistor, and this has some value V sub S and this is some value R, you can change that as long as you hook it back up to the circuit properly. You can replace that with a current source and a parallel resistance where the resistor is still R and the value of the current source is Vs divided by R. And you can go back and forth either way that you want to. And that is not completely new news, because that's the kind of thing that we found. You know, if you have a Norton equivalent, you can find the Thevenin equivalent and vice versa. And we had these things in terms of the open circuit voltage and the short circuit current, and they're related by our Thevenin. So that's what we had before. But there is a more, I guess, general way of dealing with circuits. And if you find a circuit where you see this kind of thing, you can change it in a relatively straightforward manner. And that is what the first good step for this problem is. Otherwise, if you look at it with most of our normal analysis techniques, so you look at this and you say, well, what if we wanted to do it as a mesh analysis? Well, shoot, this thing is shared between two different loops, and we're going to end up having to do a super mesh. I mean, we can do it, and I know I did at least one of those in the homework, but I'd rather not if I can get away with it. Same kind of thing up here. If I do a nodal analysis, I'm going to need at least one supernode up here, and I'd rather not do that either if I can get away with it. But what I can do is I can take this current source with a parallel resistance and turn it into a voltage source with a series resistance and change the circuit so that it looks like this instead. Let's draw it as the box. So this is kind of what I'm taking this part of the circuit and replacing it with this thing down here. Now the impedance will stay the same. It will still be a 1 plus J1 impedance that we saw from those two circuit elements. The value of the voltage source will be V equals IR. So multiply the current source times the impedance, and that will give you the value of the voltage source. And that is, in a cheap way, we can say, well, it's 2 times 1 plus J. And that's the voltage that's being put out by that voltage source. Now what makes that nice is now if I start drawing in the rest of the circuit, now it's just a single loop circuit. And it's fairly easy to analyze. Otherwise, we would have had to write some fairly confusing mesh equations or node equations, either way. Does that make any more sense to you? I have no idea. I don't really like source transformation for the most part. I think that it requires too much of the visual skills that I tend to lack. But we can write a KVL equation around this loop. So we have negative 2. Make it 2. Let's go ahead and distribute that out. So it's negative 2 plus 2J. That's the voltage source, plus I times 1 plus J1 minus 6 at an angle of 0 plus I times 1 minus J times I equals 0. So we can kind of easily see that this J1 and this cancel out as a positive and a negative. And when all is said and it's kind of simplified out, you've got that 2 times I equals 6 at an angle of 0 from this source plus 2 plus 2J from the other source. And simplifying that out, you get that the current running around there is 4 plus 1J, or 4.12 at an angle of 14.04 degrees. And the point of doing that is now that we know what the current is, we can still kind of picture where the open circuit voltage is. And if we can find out what the voltage is across these two, the resistor and the capacitor, we'll know what the voltage is across the open circuit. And that will be the open circuit voltage equals basically the current I times 1 minus J1. So that's 4 plus J times, or J1, times 1 minus J1. And plug that in just to make sure we get the right answer. 4 plus J1 times 1 minus J1. Sure. So in the kind of the nice way of expressing it is 5 minus J3. And as a phasor, that's the very unfortunate 5.83 at an angle of negative 30.96. So that's our open circuit voltage. Now we need to calculate the Thevenin impedance, since this is just a circuit with independent sources in it. So let's zero out all of the appropriate sources. What you should see, especially if we continue to look at it from the point of view of this transformed version of the circuit. This voltage source gets shorted. We have this 1 plus J1 impedance. that voltage source gets shorted. Here's one terminal of our load, and then we've got the other impedance over here, which we can characterize as 1 minus J1. And so that's where we're looking to find our Thevenin impedance, and I guess rather than calling it R Thevenin, it should really be Z Thevenin. And so those are, I think, pretty clearly in parallel with each other. So the Thevenin impedance is 1 over 1 plus J1 plus 1 over 1 minus J1, and all of that flipped. And we've calculated that once before when we were doing our superposition problem. We combined the same impedances in the same way, and that should just work out to be exactly 1 ohm. So what we will have then is a circuit where we have a voltage source that is putting out 5 minus J3 volts. We have our Thevenin impedance, which is 1 ohm. And then we can hook up our load back up, which was another 1 ohm resistor. The voltage divides evenly across the two of those, and so it's going to be 5 minus J3 divided by 2, and that is 3. Conveniently gives us back the same answer again of 2.92 an angle of negative 30.96. So it all works the same way, and the only kind of weird trick that we did in this one was to use that source transformation to get away from having to do a more complicated analysis, I suppose, of the circuit to find the open circuit voltage. But everything else, all of those same kinds of procedures just work. Let me do at least one version with a dependent source, and then I think we need to move on to make sure that there's plenty of time for various things. So, all right. So here is a source. Let's see which one I want to do. I think I would like to do the nodal or the mesh analysis on this one because, man, the Thevenin or the nodal analysis is awful. So here's our dependent source circuit, just so that you've seen one and that you realize that there's nothing really different in the way that we attack this problem, just because it's an AC circuit. So that's the makeup of the circuit. We continue to use our ridiculous negative J1, J1, 1, 1, 1. So all of the impedances are real simple. This is a 4 amp source, and this gives off 2 IX, where IX is the current that's flowing through over here. So that's the circuit. So let's do a mesh analysis because that one seems to me to be just as easy as anything else. So here's current I1, here's current I2, current I3, current I4. A couple of them are nice and easy to deal with. I2 goes the opposite direction as our source, so that's going to just be 4 at an angle of 0 degrees amps. And I3 is constrained by the dependent source to be 2 times IX. The last thing that we need to do before we can start writing the mesh equations is to write the controlling equation for our dependent source. IX is this current flowing here, which will be I4 minus I2. So we can also stick that in up here and say that's 2I4 minus 2I2. And you could further simplify this if you wanted to as, I guess that'll be 2i4 plus 8 at an angle of 0. If you want to get rid of I2 already and try to get it out of the equations. Okay, so now we can start writing our loop equations for the other couple of loops. So for loop 1, we've got negative J1 times I1, and that voltage needs a value. That is a 12 at an angle of 0 degree volt source. Kind of helps. Plus 12 at an angle of 0 plus 1 times I1 minus I3 equals 0. So there's our first loop equation. We can skip I2, we can skip I3. We write our, for loop 4, so we got negative J1, or sorry, positive J1 for the inductor times I4 minus I3, and then 1 times, well, it'll just be I4 minus I2. And then another I4, 0. All right, so we can try to simplify these things. So this equation would simplify to, so we've got a 1 minus j times I1, 1 minus j1 times I1. We've got a negative I3, and that should equal negative 12 at an angle of 0 degrees. So that should be enough to stick into your equation solver or whatever. The second one, let's see, we've got a negative I2, so that'll be positive 4. Well, I guess we can do what we can here. So the negative I2 would turn into a positive 4 at an angle of 0. The I3s, we see there's just the J1 times I3. 1 times I3. And then times I4, we've got 1 plus, actually 2 plus J1. And so we can simplify that one more time and say we've got J1 times I3, which is that nasty quantity up there. So J1 times 2I4 plus 8 at an angle of 0. Plus 2 plus J1 times I4 equals negative 4 at an angle of 0. Yeah. So we have 1, 2I4, and then a positive J1. So. Okay, so multiply out, distribute out that J1 so we can try to get this simplified somehow. So that will turn into, let's move over a little bit. And so we've got, let's make sure we do this right. I always mess up on this complex math. That just should be, if you have 0 times 2. Yeah. So we get J2 times I4 plus, if we multiply J1 times 8 at an angle of 0, we should get 8 at an angle of 90. So that is just distributing that J out, and so then we've got plus 2 plus J1 times I4 equals negative 4 at an angle of 0 degrees. So we can subtract that 8 from both sides, and this should turn into a 3J3. Or 2, so this should be 2 plus J3 times I4 equals, we have negative 4 at an angle of 0 minus 8 at an angle of 90. Whoops. Well, that's not a nice number. Hopefully this works out right. Leave this as negative 4 minus J8. So divide both sides by 2 plus J3. And so I4 should equal, and I'm a little worried about this, but divide by 2 plus J3. Yeah. I've messed up in my math someplace here.
As well, because it should be quantity 2 plus J1 compared to J3 times I4.
So, is this the step where the error's at?
I'm saying right below that you have 2 plus J1 times I4. Down below that you took away the quantity. So you had 2 plus J1 times I4. So it's just J1 times I4 plus 2.
So,
Like that.
I don't know that should
Yeah. I don't know.
should matter. The one thing that I'm seeing primarily in my math earlier in this version is that this wasn't negative quite so early, but so my notes are kind of rough here. So we had negative J1 times I1 plus 12 at an angle of 0 plus 1 times I1 minus F equals 0. So this doesn't even really affect us a ton. The thing that we're trying to solve for in the first place is the voltage across this 1 ohm resistor. So if we can find out what I4 is, then that's all we really need to find out anyways. So we don't even really need to worry about this a ton. But let's rework. See if we can double check this work at least a little bit. So we have J times I4 minus J times I3 plus I4 minus I2 plus I4 equals 0. So try to collect the terms. We've got negative I2. On I3, we've just got the negative J times I3. And then on I4, we've got 2 plus J times I4 equals 0. So negative I2 should give us 4 at an angle of 0 degrees because I2 was a negative 4. This is J times I3, and I3 is 2I4 plus 8. plus 2 plus j times I4 equals 0. Oh, you know what what was probably the problem? It looks like I lost a j3 somewhere. the negative j, I think, yeah, up here this turned into plus j1 times I3. So that's where the error is. So let's see if I can just kind of copy my notes and get the right answer now. So where are we here? Well, the 4 goes onto the other side as a negative 4 at an angle of 0. We get negative j2 times I4. If we multiply negative j times 8, 0, 1 times 8, yeah, that gives us 8 at an angle of negative 90 degrees, which I think is also more right. But we can also just say it's negative j8 plus 2 plus j times I4. So add the j8 to the other side. Combine the j2 stuff here, and so that should give us, yeah. So now we're down to 2 minus j times I4 equals negative 4 at an angle of 0 plus j8. Divide both sides by 2 minus j. And I4 gives us 4 at an angle of 143.13 degrees. That's what it should be. We'll just double check. We have negative 4 at a second angle of 0 plus j8. Divide that by 2 minus j. And let's just make sure. Yeah. This actually, when you run the numbers in rectangular mode, should give you 3.2 plus j 2.4, which translates down to that. So the place that you will screw up on AC analysis is in the complex math. And that's where I screw up too. I have to be so very careful when I do these problems to make sure that I don't mess up on the math. So what I will do for this problem is I'll write up all of the math for the rest of the problems as an independent, with nodal analysis and as a Thevenin analysis. Post that on the website for you to take a look at. If you have any questions, you can ask about it in class on Monday. Very briefly, shouldn't be much of a problem. We'll take a quick look at what I expect to see on the exam. So let's close this one, go to the top. All right. So stuff that might be on the exam for Monday. We'll try to give you a clear idea of what's going to happen here. On the last exam, we did do Thevenin equivalence, but we left out the dependent sources. I gave you one quiz question with that material on it, and I think I'll give you one more on the exam. I don't think, just as a reminder more than anything else, if you do have a circuit that contains only dependent sources, the only way to find out what the Thevenin equivalence of that is, and the Thevenin equivalence is just the Thevenin resistance, you have to hook up a test source and determine the other parameters. So if you hook up a voltage source, you find the current, or vice versa. If you have a mixture of sources, you need to calculate the short circuit current and the open circuit voltage, take their ratio to find the Thevenin resistance, and then you can do whatever you want to do. So I will probably put together a simple, as simple as I can, something on the order of the difficulty of the quiz, and perhaps, yeah, it's going to try to be no more difficult than that for a Thevenin problem. So expect to do one more of those. For chapter 6, that was looking at the capacitor and inductor stuff. I'm not really concerned about these things a ton. The only problem that you might see coming out of this would be something similar to the kinds of problems that you saw from chapter 6, where you do some combinations of inductors or capacitors, or a question like, so if I have these 3 capacitors, can I combine them in any order to get some other capacitance value that I want? Probably the most key thing to take away from the chapter is what is the behavior of a capacitor and an inductor under DC conditions. The capacitor acts like an open circuit. The inductor acts like a short circuit. So those are the key things there, I think, more than anything else. But in chapter 7, we looked at first and second order circuits. There's a lot of stuff on here on exactly what the problem solving technique is. You can go ahead and review that, make sure you're comfortable with it. We just did an example at the beginning of class, draw the circuit at time equals 0 minus, with this idea that it's been there for long enough, and so the storage element has assumed its steady state condition. Take and then solve for that, the voltage across the capacitor or the current through the inductor. Run with, then draw the circuit at time equals 0 plus after the switch is actuated. Replace the storage element with the appropriate independent source, whether it's a current source or a voltage source. Solve for the initial condition on the whatever it is that you're looking for. Draw the circuit at time greater than 5 tau, replacing the circuit elements again with the appropriate steady state behavior. And I think what people will continue to do, and what perhaps even occurred on the quiz, was said, okay, well, there was a current source here that was acting, the inductor was acting as a current source, and then when we start doing like Thevenin resistance and stuff, that's when we pull out the current source and it turns into an open source or an open circuit. And that's, I think, was the problem. We have to make sure you're thinking, okay, the steady state behavior of an inductor is to short circuit, and when it's just after a switch actuate, it acts like a current source. But when I'm doing a Thevenin resistance and I'm zeroing out a current source, that's an open circuit. And just make sure that those 3 things are very distinct in your mind, so that you don't think, well, it was acting like a current source, and so when it's not acting like a current source anymore, it acts like an open circuit. It doesn't. It acts like a short circuit. But just make sure that you kind of keep that straight. So then you do zero out all the sources, find the Thevenin resistance, and then either multiply that by the capacitance or divide the inductance by the resistor to find out what the time constant is. Solve for the constants K1 and K2, and you will have the circuit. For second order circuits, what you will probably see is something very similar to the kinds of questions that you saw in the homework, where there might be some amount of initial conditions to do a little bit of circuit analysis for, but the likelihood is that I will just write a question where you're given initial conditions and you kind of run with it. The circuit parameters will be chosen so that it will either be underdamped or overdamped or whatever. You do need the 2 initial conditions, and normally that's going to, for the parallel circuits, that's going to be the voltage across the capacitor and the current running through the capacitor. From chapter 8, you should be able to take a function from a time function to a phasor and back, depending on the frequency of the signal. You should be able to take and calculate an impedance or an admittance, probably an impedance. That's what the quiz looks like. Calculate an equivalent impedance. And then I can ask you to do any kind of AC analysis. Probably would just be one of the more simple, straightforward ones. Do a mesh analysis or a nodal analysis on something where it's a fairly straightforward circuit, because we haven't done a lot with those yet. But almost certainly won't put a Thevenin AC circuit on the exam, because that's just mean. at least for this one. You might see a Thevenin AC circuit on the final, but yeah, that would be about it. Formats will be very similar to the last exam, where you do a couple of the problems just a little ways. So I might give you an AC circuit and ask you what the Thevenin resistance would, or the Thevenin impedance would be if you're going to do it as a Thevenin problem, or just ask you what is the time constant for the circuit as drawn. So all you have to do is take a look at what the circuit looks like when the switch has done its change, zero out the sources, and find out what that is. And so you're not actually doing the full-blown first-order analysis. You're just finding the time constant. Or I might ask, if these are the values of the circuit of a parallel RLC circuit, is it overdamped, underdamped, critically damped? What is going on with the circuit there? I will do my very, very best to make the exam take no more than 50 minutes or so to do, but you do have an hour and a half to work on it, so you can take as much time as you want. I'll give you all of the formulas, at least in terms of the forms of the responses for the circuits. The only thing that I won't tell you is what the relationship between omega naughts and alpha is that gives you the appropriate kind of damping. That's, I want you to remember at least a little bit. I'll post what the actual formula sheet will look like sometime in the next couple of days so that you have an idea of what you do have to remember and what you don't have to remember. And last thing, time and place, it's going to be Monday, 6 to 7:30. Going to be in IRC 214, just the same place we were last time. So if you have any questions about the material that's going to be on the exam, please feel free to ask those on Monday. If you don't ask questions on any of that material, we're going to go ahead and move on with power, which is definitely my least favorite part. I'm glad that there are people out there that like power because I like having lights in my house and stuff, but that is definitely my least favorite aspect of all of electrical engineering, with bar none. So, but we will try to keep it, get you ready to see maybe you really like power and you'll want to go in that direction, because we do have a really excellent power faculty and program here. So, so again, if you have any questions about what's going to be on the exam or something, let me know. Otherwise, we're going to go ahead and do this quiz. Okay.